In the last video, we took a look at the concept of differentiability and had that big, scary definition. Ultimately, though, keep in mind that there were three implications that we wanted to be true if a function was differentiable at a point. We wanted to have a tangent plane that was non-vertical. The tangent plane should approximate the surface pretty well, at least near the point of tangency. And we should have that if a function is differentiable at a point, it's continuous at a point. That's what we want. And fortunately, that above definition actually gives us these particular things. You'll see here that this first theorem states that if a function is differentiable at a point, then it must be continuous at that point. And again, this is very similar to what we saw back in Calc 1, and we actually should be thrilled to death that we have this extension. It's always nice when we can have things that kind of line up and are very, very similar as we continue to kind of move up dimensions. Now, even with all three of those kind of implications of differentiability, if all we have is this scary, scary, scary looking definition, it actually ends up being functionally pretty difficult to show that a function is differentiable at a point. So this is where our second theorem comes in. How can I actually guarantee that a function is going to be differentiable at a point without having to go through the big scary definition that's really hard to use? Okay, well here's what we have. It's actually really simple. Let's suppose that I calculate all first order partial derivatives. So like for a two-variable function, that would be I calculate the partial derivative with respect to x and with respect to y. But if I had a function that had more input variables, I would have to compute lots of different partial derivatives, maybe for x and y and z and w and k and like for all the different input variables. But let's suppose I compute all of those and they all exist at a particular point. None of them come out undefined or anything like that. And they all represent continuous functions at that point. If those two things are true, then we can absolutely guarantee that f is going to be differentiable at that point. So let's take a look and see how that actually plays out in something simple here like example 1. Is this function differentiable at the point 1, 1? Well, let's go ahead and see. What I would have to do again is compute my partial derivatives and confirm that they exist at the point 1, 1. So let's see, here my partial derivative with respect to x would be 1 plus, and then I would have to do, let's see, a 1/2 x plus y to the negative 1/2. Chain rule, take the derivative of the inside. Since I'm going with respect to x, y is going to be treated like a constant, so I get 1 plus 0. If I was to rewrite this so it's just a little bit cleaner, I have 1 plus 1 over 2 times the square root of x plus y. Notice that if I was to try to plug in the value of 1, 1 here, I'm never going to get anything that's undefined. So f, its partial derivative with respect to x, definitely exists at the point 1, 1. Similarly, if I was to go ahead and compute my partial derivative with respect to y, I think I'm going to end up here pretty much with the exact same thing, except that I just won't have that 1 out front. I'll just have the 1 over 2 and the square root of x plus y. Again, I can see that if I was to evaluate this at 1, 1, I definitely end up having a value that pops out, implying that my partial derivative exists at this point. I could also definitely see, though, that these functions here represent continuous functions, except at the point where x and y end up being opposite values or equal to 0, in which case I would divide by 0. Certainly, of course, that does not happen at 1, 1, and so I can say that f, my partial derivative with respect to x at 1, 1, and partial derivative with respect to y at 1, 1 exist, and the partial derivatives are continuous here. They are continuous at 1, 1. So this means that f of xy is differentiable at 1, 1. There it is. we can easily go ahead and confirm that a function is differentiable at a point by simply doing what this theorem up here says that we can do. So if you're ever asked in the future to show that a function is differentiable at a point, you could go ahead and attempt to use the same technique that we did here. This is really all that we need to know for the moment about differentiability of surfaces for our two variable functions here in this class. So make sure that you feel comfortable with what's happening here. And of course, if you have any questions, feel free to reach out to me.